Okay, I want to introduce one last definition in our unit on derivatives here. This definition is concavity. And for concavity, notice we have these notions of concave up and concave down. I want to talk about those visually before we relate them to our derivatives here. So I like to think of these just in terms of parabolas. So concave up means the graph opens upwards, so it's like a happy parabola, right? Concave down means the graph opens downward, so it's a sad parabola. So that's what these words mean, right? In plain English, is just which way does the graph open? And that's not super profound just yet. I want to talk about how this relates to the derivative, and then we'll look at an application of like why this is useful. So notice in my definition of concavity, my test for concavity, these both have f double prime in them. That's how you read that. So this is the second derivative or the derivative of the derivative, right? So f prime is the derivative of f. F double prime is the derivative of the derivative of f. And that's what tells us whether a graph is concave down or concave up. So why is this useful, right? It's not just to tell what the shape of the graph is. It actually can tell us a lot about how something is behaving in real life. So in this example, we have a flu virus, and we have a function modeling how it's spread. This is a version of a function that scientists actually use to model these things, by the way. And we're going to look at the derivative of f prime, and then the second derivative of f double prime here. And this is an ugly function, so what I'm going to do is I'm going to use my calculator to fill out this table, and then we're going to talk about how it looks on the graph. So what I did is I typed in the derivative of my function into my grapher, and I let x equals x, and then I hit this variables button, and I put in my function y1 into the second line of my grapher, and took the derivative of that. So y2 is the derivative of the derivative. And then I'm just going to use this table button to fill it out. I did go through that pretty quick, but you're welcome to use your calculator to try to reproduce those values. It's a nice little trick to know. So I filled out the table using just the values off of my calculator, and I noticed two things. First is that f prime of t is always positive, right? So greater than 0 always. That means f is always increasing. And we can see that from the graph, right? Pretty clear that f is always increasing. But f double prime switches signs here between 11 to 12, right, in this interval. So at that point in the graph, what we see, right, is on the left, f double prime is positive, and on the right, f double prime is negative. So that means we have a concave up region and a concave down region. And writing these in words is really why we're looking at this graph. So what does this mean? Remember, we're talking about cases of the flu. And what we're talking about is the derivative of the derivative of cases of the flu. So on the left, what this tells us is that cases are increasing, and the rate of increasing is increasing as well. So increasing at an increasing rate. So it's getting worse, and it's getting worse faster, right? On the right-hand side here, though, where my second derivative is negative, I would say cases are increasing at a decreasing rate. So cases are still getting up, but they're increasing at a slower rate. So it's getting worse, but it's getting worse slower, right? So during the pandemic, we heard a lot of this language, right? Like the flatten the curve. The second derivative is what tells us whether the curve is getting flatter or not. So that's really why this is useful to us, is not because it tells us the shape of the graph, but it tells us how our rate of change is changing in a certain phenomenon. Let's look at an algebraic example. So these are going to be more similar to the problems you're going to have to solve. So what I'm asked to find is an interval where f is increasing. Oops, and I would annotate this. If I had it on paper, right, I would say increasing means f prime is positive, and concave up. Well, from my definitions at the top of the page, that means we want f double prime to also be positive. Okay, so clearly I have f, I need both f prime of x, and then I'm going to use power rule, and I'm also going to need, we'll do this one over here, f double prime of x, which is going to be just the derivative of my derivative. So I'm going to take the derivative again, and this is all going to be very familiar at this point in your calculus career. And then I'm going to make a sign chart for both. So I can set both equal to 0 and factor both. And the order you do this in does not matter. Here I factor out a 4x. I get only 2 zeros, which is nice. So I get x plus 3 and x plus 3. And then I need two sign charts, right? So I'm going to line them up nice. So here's going to be my 0 for both, right? And I have an f prime sign chart. Labeling these is super helpful so you can keep what you're doing straight. And f prime had zeros at -3 and 0. And then f double prime had zeros at -1, which is between -3 and 0. And also -3. So notice those can be the same, and that's okay. And then when I plug in points to check, I'm going to plug in for this sign chart to f prime of x. So I'm going to use this guy. And I get negative, negative, and then positive when I test points. And then for f double prime, same thing. I'm going to use this guy when I plug in points, and I get positive, negative for between -3 and -1, and then positive again. Now, my last step is to just think what I've been asked, right? So I want increasing and concave up. That's why I annotated this. So I want my positive second derivative and my positive first derivative. Well, I know my increasing interval is from 0 to infinity, and that's based on my first derivative. My concave up intervals, well, I have 2, right? But the one I only care about is to the left of -1. So concave up, well, I would say from -infinity to -3, and then from -1 to infinity. But where they overlap, the answer to my question is here, right? From 0 all the way to the right. So my solution, increasing and concave up, well, that would be from 0 to infinity, because I only want where both of my statements are true. What the graph looks like, this is a great thing to end on, is this, right? So we see my graph is both increasing from 0 to infinity and opening upwards, right? So that is it. Notice it's super similar to our velocity problems and allows us to talk about new things that we could not talk about before.